Um, it's my pleasure to introduce Willie Neiswanger today, who is going to tell us about Bayesian Algorithm Execution. Willie, we're very happy to see you at our seminar, and I give the floor to you now.
Okay, great. Thank you so much for the invitation. Great to be here. So my name is Willie. I'm a postdoc right now at Stanford University, and just make sure my slides work. This is joint work with my collaborators Alex Wang and Stefano Erman on a project called Bayesian Algorithm Execution. And the one-line summary of this project is that it's about extending Bayesian optimization from estimating global optima to estimating other function properties that are defined by algorithms. Okay, so first I'm going to give a quick background on black box global optimization. So suppose that we have a noisy black box function f, where you can query f on an input x and observe an output y. And we're going to assume that our observations y are noisy. Each function query on an input x is costly, for example, in money or time, or maybe human labor. And the goal of black box global optimization is to estimate the location x star, let's say, of a global optima of f, given a budget of t queries to f. So black box optimization has many applications. For example, in the area of machine learning, where I work on a lot, there's a number of applications to hyperparameter optimization of machine learning models, as well as neural architecture search, designing neural network architectures. More generally, in systems auto-tuning, there's a number of applications to tuning configuration parameters of various computer systems. In the sciences, in particular at national labs, there's a number of applications for optimizing laboratory equipment and machines. For example, here I'm showing some examples on optimizing performance of particle accelerators or tokamak machines in nuclear fusion. Finally, in materials discovery and protocols, there are a number of applications, for example, in catalyst design or battery charging protocols, that all can be viewed as a task of black box optimization. And a popular methodology for approaching this task is known as Bayesian optimization, which leverages a probabilistic model of f to sequentially choose queries in an efficient manner. So this probabilistic model can incorporate prior beliefs about f, for example, its smoothness, and it can tell us where we're certain versus uncertain about the value of the black box function f in order to allow for sample efficient optimization. So the main motivation behind this project is that in a variety of real-world tasks, there are many other properties of black box functions beyond global optima that we might also want to estimate. So for example, there are a number of variations of optimization where you want to estimate things like local optima of a function with respect to some initialization point, or maybe the top k optima of a black box function. In multi-objective optimization scenarios, we often want to estimate the Pareto frontier amongst multiple objectives of a black box function, multiple outputs. In tasks of level set estimation, oftentimes you want to estimate a sub-level set or a super level set of a function, which is a subset of the domain where all the values in that subset are below a given threshold or above a given threshold. For example, I've approached this task in applications such as catalyst design and active learning. In search tasks, you often want to find a subset of your domain where items under the black box function have a value that matches some criteria, for example, in drug discovery or fraud detection. In tasks of phase identification, you often want to identify boundaries within your domain, or you want to partition your domain into subsets, for example, in high throughput materials design and discovery. In root finding tasks, you want to find the elements in your domain that equal 0 under the black box function. Quadrature is another popular task where you want to estimate integrals or expectations or averages of your black box function. There's many times where we have a function defined over elements of a network. So for example, over nodes or edges in a network. And in these applications, you might want to estimate properties of the network. And this can be viewed as a property of a black box function that you might want to estimate. Finally, in sensor placement problems, you often want to find the value of a black box function over multiple locations on a domain. So the goal of this work is to develop methods to estimate a broad set of function properties within a limited budget using probabilistic models. And you can view this as a generalization of Bayesian optimization to other function properties beyond global optima. So the first question we want to tackle is, how do we formalize this notion of other function properties? And we actually formalize this in terms of viewing them as the outputs of algorithms. So specifically, note that if you have a function property of interest, there often exists effective algorithms for either computing or numerically approximating this property if you were to ignore your limited budget constraint. So for example, let's suppose that we have a black box function and the property we want to estimate is a local optima of this function with respect to some initialization point. Okay, so what we can do is we could run some local optimization algorithm. So for example, gradient descent or the Nelder-Mead method or an evolutionary algorithm, which essentially start from some initialization point, and then you run a local minimizer, which takes a sequence of queries on your black box function, and then finally converges to some local minima, let's say, and returns the minimal found value as an output. So this is an algorithm that exists, a local optimization algorithm for computing this local minima property. That's what we're interested in. So let me give another example. Suppose the property that we care about is the super level set of F. And in particular, let's suppose that we have a discrete domain of points. So there exists an algorithm. For example, let's suppose that our discrete domain is the set of blue points here along the x-axis. So what we can do is we can scan through each of these blue points. For each one, we can query its value on this black box function, which is this thick black line here. The queries are shown in pink. And then after scanning through all of our points in our domain, we can take the subset of points whose value is above the given threshold. This is, the scan and query algorithm is a way of computing this super level set in this case. And let me just give one more example. Suppose the property of a black box function that we care about is an integral or an expectation of f. So there exists a variety of numerical integration approximation algorithms for approximating integrals, for example, a rectangular or a trapezoidal approximation. And in this case, to compute the property, we could run one of these numerical integration algorithms over our domain, approximately compute the integral and return that as output. So this is, another example of an algorithm that exists for computing the property if we're to ignore the budget constraint. Okay, so in general, we define a computable function property to be the output of a given algorithm A if we were to run the algorithm A on our black box function F. And so all the previous examples that I gave on the last few slides are all computable function properties, including local optima, integrals, level sets, Pareto frontiers, partitions, etc., and many others. Essentially anything that can be viewed as the output of an algorithm that you run on your black box function. And I'm going to define Bayesian Algorithm Execution, or BAX, to be the task of estimating a computable function property, or equivalently, estimating the output of an algorithm A using a budget of only T queries to F, even if the algorithm requires far more than T queries to actually execute if you were to run it on your black box function. Okay, so notice here that we're framing a function property in terms of an algorithm, and there's two main reasons for this. The first one is that it gives us a very fine-grained way to define function properties. We parameterize basically a function property with respect to any algorithm. And second of all, we're actually going to use this algorithm that parameterizes a function property in a procedure to efficiently estimate these properties using probabilistic models, which I'll get to in a second. Okay, so getting into methods for Bayesian algorithm execution. So in particular, we've developed an information-based method for Bayesian algorithm execution called InfoBAX, which is based on information theoretic methods for Bayesian optimization. So first, some background on this. There are a few popular information-based methods for Bayesian optimization. For example, methods called entropy search or predictive entropy search or max value entropy search, each of which is rooted in Bayesian optimal experimental design, where the main idea behind Bayesian optimal experimental design is that if you have a probabilistic model with some unknown parameter of interest, you want to choose some set or sequence of experiments that most reduce the uncertainty about this parameter, where the uncertainty is often taken to be the entropy of a posterior distribution over this parameter. So to describe our Infobacks procedure, I'm first going to describe these information-based Bayesian optimization methods and then extend it to Bayesian algorithm execution. So here's a standard algorithm for Bayesian optimization. As input, you start with a data set of XY pairs, so observations from your, from your function, previous function queries. This could also be the empty set, as well as a model for your function f, in particular, a prior distribution over f. And then over a sequence of t iterations, you do the following at each iteration. You first optimize an acquisition function, which is a function defined on your domain in order to return a single domain point. So this acquisition function here is denoted as alpha. And the intuition is that the acquisition function is, you're trying to define it in a way so that it captures the value of querying your black box function f at a given x. And it's usually defined using our probabilistic model. And again, when you optimize this, this returns at a given iteration t, it returns x sub t, which is the next x to query. You then query your black box function on the chosen x and observe an output y. And then you add this xy pair to your data set and you iterate through t iterations and either return the estimated optimal point or just in general the final data set at the end of the day. Okay, so visualizing this, here I've drawn an unknown black box function f, which is the thick black line, and a data set of xy pairs, which are the black x's. So given this data set, we can infer our function f using a probabilistic model. So here in the gray band is the posterior of the posterior distribution over functions. And I've sampled a number of times from this posterior to draw each of these colored curves on the screen. So each of these are samples from the posterior distribution over functions. Based on this probabilistic model, we can then define an acquisition function here. I'm showing just a simple acquisition function, which is popular in Bayesian optimization, called the upper confidence bound, or UCB, but there's a number of popular acquisition functions. So you define this acquisition function using your probabilistic model, and then you want to optimize this acquisition function to get the next point to query. So if we do this, we find the next point that we think has most value based on this definition of our acquisition function. We then query this point, get a new observation y, and we add this xy pair to our data set. So that's the usual one iteration of Bayesian optimization. Okay, so the key step here really is line 2, which is defining and then optimizing the acquisition function. So going back to our...
excuse me, I wanted to maybe add a quick comment that in the previous slide, what's called acquisition function is not exactly the thing that was shown on the slide with function, because here the acquisition function also involves like learning the probabilistic model. And here acquisition function operates, I think, when you already have acquisition, when you already have probabilistic model.
Yeah, so this acquisition function here in blue, right, is defined using this probabilistic model denoted as this gray band here.
Yeah.
Okay. Yeah. Yeah, so this guy here is defined on top of whatever data set you've collected so far. Okay, so so describing the particular acquisition function for information-based Bayesian optimization. Going back to this diagram here of the probabilistic model and the samples from this posterior distribution over functions. Okay, so you can consider the global optima, the global maxima, let's say, of each function sample that I've drawn here on this slide. Okay, so let's suppose we denote each of these as a red dot, and I plot them on the screen. So these are the 6 optima of the 6 functions I've drawn here. So in general, you could consider that there's a posterior distribution over global optima that's induced by our probabilistic model on the functions. And I'm going to denote that of each of these global maxima, let's say, as x star, and this distribution as P of X star given our data set so far. Okay, so this distribution over these red dots is going to be pretty important for the definition of the acquisition function in information-based Bayesian optimization. In particular, this leads us to the acquisition function that's used in entropy search methods or predictive entropy search methods, which is the following. So this is the acquisition function for a given input X, and I'm going to describe the couple of terms here. In the green box on the left, this is the entropy of the posterior distribution over the global Optima X star. So this is the entropy of that distribution over red dots that I just showed, minus the expected entropy of the posterior distribution over global Optima X star if we were to make a query at a given X. Okay, so this is the expected information gain acquisition function. It's the expected decrease in entropy if we were to query F at a given X. And there exists a clever way to compute and then optimize this from work on predictive entropy search, which I'm going to describe. It basically breaks down the acquisition optimization procedure into two stages. So before acquisition optimization stage, where you pre-compute some stuff, and then during acquisition optimization. So before acquisition optimization, you want to generate a bunch of posterior samples of the global Optima's X star. So you want to generate these red dots. So typically what you do in practice is you run some sort of global optimization algorithm on posterior function samples to produce a lot of these maxima, and then you store them. And then during acquisition optimization, for any X, you can then approximate the expected information gain using these pre-computed samples. And you can do it pretty cheaply. And because we can do that, we can then optimize over this approximate expected information gain using some sort of zeroth order optimization procedure. And the benefits here of breaking it down into these two steps is that we only have to run the global optimization algorithm on function samples in order to generate our optima once before acquisition optimization. You have to run it once per sample, but you only have to do this before acquisition optimization. And then during the acquisition optimization, which is an iterative procedure, it's cheap. You just use the same pre-computed set of global optima. Okay, so the previous was work on information-based Bayesian optimization. So now I want to relate it to derive the acquisition function for our InfoBAX technique. So recall that the goal of Bayesian algorithm execution is to estimate a computable function property using a limited budget of queries, or equivalently to estimate the output of an algorithm A using a limited budget of queries. So similar to information-based Bayesian optimization, we're going to take a Bayes optimal experimental design strategy where we denote the output of our algorithm A, which parameterizes the property we care about, the computable function property, as O sub A. And we're going to care about the posterior distribution over this output that's induced by our probabilistic model. So P of O sub A given our data, and in particular, the entropy of this posterior distribution. And our goal is, similar to the previous case, we want to make queries to best reduce this uncertainty, this entropy, over the algorithm output. So we can also define an expected information gain acquisition function in this case, which is the following, and I'll again describe the terms. So in the green box on the left side, we have the entropy of the posterior distribution over algorithm outputs, excuse me, minus the expected entropy of the posterior distribution over algorithm outputs if we were to make a query at a given X. So this is the expected decrease in entropy, or the expected decrease in uncertainty on the algorithm output if we were to query our black box function F at a given X. Okay, so how do we...
The only thing that's changed is that the result of global optimization is now the result of algorithm evaluation, yes?
Correct. So yeah, and you'll see a second algorithmically how this will be modified a little bit, but in terms of the formula here for the acquisition function, the key thing is that before the O sub A's were X stars. So before it was reducing the entropy about the location of the global optima, and now we've replaced the value of the output of the algorithm instead of that location of global optima in this formula. Great. Okay, so to describe how to compute and optimize this, I'm first going to introduce one more thing here, which is the execution path of an algorithm A. So I define the execution path to be the sequence of queries or XY pairs that the algorithm, the computable function property algorithm, would have made on the black box function f if we had run it on the black box function f. Okay, so taking this this local optimization example from before, if you remember, this algorithm initialized at some point, it made a sequence of queries, and then it converged to some local minima. The sequence of pink dots would be the execution path of this algorithm. Or similarly for the super level set example that scanned through each of the discrete domain, which is the blue points, and queried each of these points and then returned the subset that had a function value above the threshold. Again, the pink dots here is the execution path, the sequence of XY pairs for this algorithm. Okay, so note that we don't know the true execution path since we're not running our algorithm A on the black box function f. As we assume that this requires too many queries and we're trying to efficiently estimate the output of A. But if we have a probabilistic model for f, we can think about the posterior distribution over execution paths. And that's going to be useful for our acquisition function. In particular, visualizing this, again, suppose we have this probabilistic model for f given our data set, where I've plotted a number of posterior function samples. And so consider one function sample, such as this green one here. We can run our algorithm A on the function sample from the posterior. And if we did that, we would get the following execution path of algorithm A on the sample here, supposing this is just some arbitrary algorithm that we've chosen that defines a computable function property. So we could do this on a number of posterior function samples. And in general, we could consider that there is a posterior distribution over execution paths that's induced by our probabilistic model. And this posterior distribution is going to be important for computing and optimizing our acquisition function. So similar to...
Willie, can I ask a question? So formally, the execution path is a sequence of pairs of x and y's.
That's right. That's right.
Is there some formalism for like posterior distribution over what? Over like sequences of different lengths? What can you say about like the formal nature of this object?
Yeah. So it would need to be a posterior distribution over sequences of different lengths. I think that formalism needs to be done to some extent. So, in the paper, we've done a little bit of this, but I think a lot of the groundwork really needs to be kind of laid out to have a more, theoretically formal like underpinning to some of this stuff.
So now we just more intuitively, we need to intuitively understand this like object. Yeah,
I was going to say this should be the push forward of the posterior distribution under the algorithm, where the algorithm is viewed as a map from the distribution into some like discrete space of with a fixed length or possibly with a variable length. I mean, this would be like a disjoint union measure space or something like this. I'm sure you can build such objects.
I think that sounds like a good way to do it. Yeah.
Yeah, it's interesting. What can we say about these objects and like what theory is behind them? But all right, it's I guess we shouldn't discuss this in the middle of the talk.
Good thing to discuss later, though. So I'll continue here for a second. Yeah. So suppose you do have the ability to draw samples from your posterior distribution and then run an algorithm on each of these to get the execution path for each posterior function sample. Here's how we use it to compute and optimize the acquisition function. So you'll note this is pretty similar to information-based Bayesian optimization in that there's two stages that you need to run similar to before. So before acquisition optimization stage and during acquisition optimization. So before acquisition optimization, you run your algorithm A on posterior function samples to get these samples from the execution path. And then you store those. And then during acquisition optimization, you can take these posterior execution path samples and use them to approximate the expected information gain. And because we can do this, we can quickly approximate the expected information gain for any x, and therefore optimize over this acquisition function by, again, running some 0th order optimization algorithm. And you'll note that this has a similar structure, what I described before, with the information-based Bayesian optimization, but we've essentially just replaced the global optimization algorithm running on each of these posterior function samples with our algorithm A that parameterizes the function property. But the computational benefits are the same, in that you only need to run this algorithm A on posterior function samples a set of times once before acquisition optimization, and then you store them, and then during the more expensive iterative acquisition optimization procedure, you can quickly compute the approximate expected information gain for any x, and then run this optimization procedure much more efficiently. In the paper, we have our math for this particular point for approximating the expected information gain using these samples. We'll also have it at the end of the talk if people are interested, though I haven't included it right here, these details.
Maybe get a rough idea of why, when we consider Bayesian optimization, we don't need the path, but here we need path to do everything efficiently.
Yeah, that's a good question. So in the here, oftentimes you have an algorithm that depends on multiple, let's say, this is just sort of like a little bit hand waving kind of intuition about it. Sometimes you have a algorithm output or a computable function property that depends on a number of locations throughout your path. And sometimes it only depends on, some maybe the final position in the path or some small subset of the execution path. But the way this estimate of the expected information gain works, it naturally sort of integrates out the parts of the path that aren't informative. So in the case where, for example, the property that you care about is actually a global optima, the approximation that you use for the expected information gain actually ignores a great deal of the path and only looks at the subsets that, in this case, would be closer to like the minima or the maxima of the function. So it actually reduces to the same thing in that case. But there are some properties where you actually do care about the function value, not just kind of at every point in the execution path. Like, for example, let's suppose the property that you cared about is the value of the function over a fixed set of points. And suppose your algorithm was scanning through all of these points and computing the value. So there, like, clearly the full execution path is equal to the property, and you care about every position on there. So you can kind of think about depending on the property and the associated algorithm, you might actually you do care about every point in the execution path. But in some properties you don't, and this expected information gain reduces to ignoring those parts of the execution path in those cases.
Yeah, I see. And maybe one quick follow-up question. So do you think for Bayesian optimization we can get some kind of improvement by maybe considering this path while optimizing the acquisition function, or is it obvious that we cannot cannot make anything useful of it?
Yeah, that's a good question. So I think there's two things to think about here. So one is I think you can get improvements based on the fact that you can consider variations on the type of property. So like one of the applications, which I'll kind of show some results for in a second, is like, suppose you really don't care about finding a global optima of your space, but you want to be a little bit more myopic and find only a local optima. Or suppose you want to find a number of global optima, or suppose you want to, estimate the output of a very particular type of optimization algorithm. So these are different types of properties that might actually improve the performance. And there, I think it can be beneficial. But let's suppose we're talking about sort of the exact same property as you'd want to estimate with like a predictive entropy search, which is sort of a standard Bayesian optimization method that doesn't use the full execution path. There, I think they're essentially bypassing some sample approximation that needs to be done here. So if you have the exact same property that you can compute it in a more closed form, it should roughly be the same result, where this one might give, in cases where you're able to compute something in a closed form, this one might give you a sample approximation and could be either the same or slightly worse.
Mm-hmm.
So to summarize, if you can estimate a different property, I think could be helpful. And for the same property, if there exists a sort of a more exact way to compute it, it probably is going to be only the same or slightly worse than that.
Yeah, thank you.
Sounds great. Okay. Right. So let me just summarize the whole procedure. This is kind of a similar structure as the Bayesian optimization algorithm before. We've got the same two inputs, an initial data set and a model for F, as well as an algorithm A that specifies the computable property that we care about. Again, over a sequence of iterations, we first optimize our acquisition function. We query the point that we've chosen as our next query point, x sub t. We add this to, we observe the output and we add this to our data set. And the only difference here is that in the acquisition function, it's now also a function of this algorithm A. And again, in order to optimize this, we do these two steps where we first run our algorithm on posterior function samples, and then we optimize our acquisition function using the resulting execution paths. So the one slide summary of kind of the full InfoBAX procedure, just to make sure it's clear. Suppose that we have this black box function F and a property of interest. So it could be a level set, maybe an inflection point or an integral or a local minima. And suppose that there exists an algorithm for computing this property of interest. So suppose we have a computable function property where the algorithm could be of any budget. Our goal is, again, to estimate the property, or equivalently to estimate the output of A with a minimal set of function queries. So we've got this InfoBAX procedure, which is the sequential algorithm, similar in structure to Bayesian optimization, where for the acquisition optimization step, you run these two stages. You first run your algorithm here on posterior function samples, and then you store those set of samples and use it to approximate the expected information gain for any X, so you can optimize over that to choose the next point to query. And then as an output, you return a posterior estimate of your property, or a posterior estimate of your output of A. Okay, so I want to show some sort of demos of BAX in practice on a few different applications. So in particular, I wanted to show 3 applications. First one is on estimating shortest paths in graphs. So if you have a unknown black box function over, let's say, the edges of a network, you can view properties such as the shortest path in graph as a property of this black box function, as well as 2 variants of optimization, in particular, local optimization, which I've kind of described a little bit throughout this talk, and a top K, an application on estimating the top K optima of a black box function. Okay, so first one is estimating shortest paths in graphs. The main idea is that graph traversal and search algorithms can define properties of a black box function that are defined on the edge weights of graph. So suppose that we have a real world transportation network, such as a network of roads, of rails, shipping routes, or air transport. And suppose we want to find a shortest path from a location A to a location B in this network. So this shortest path depends on the edge weights in the network. For example, based on these transportation networks, it might depend on the traffic on the roads, or maybe road conditions, or weather, or maybe shipping costs, or otherwise. And it could be, in practice, quite expensive to query edge weights. For example, you might need to measure traffic or road or weather conditions via a satellite, or you might need to determine or maybe even negotiate shipping costs between two locations in your network. So the goal here is to be able to adaptively query the edge weights in order to estimate the shortest path in this network efficiently. So as a demo, suppose here that we have a grid-shaped graph with 400 nodes and about 3,000 edges. And so just to be clear, each of these circles here is one of the nodes, and you can see that each circle is connected with its adjacent neighbors, both in the up and down, left, right, and diagonals, though these edges are pretty light on this plot. And suppose that the edge weights are given by an unknown black box function here, which I'm denoting in green. So every edge here is given a weight value depending on the value of the black box function at the center of the edge in this case. Okay, so suppose we want to know what is the shortest path between a goal node, which is the purple box, and a start node, which is the purple box, and a goal node, which is the yellow box. So just showing you what the shortest path would be under the set of edge weights given by this green black box function. So this is the true shortest path between the start and the goal node in this graph. And again, you can view this shortest path as a property of the black box function over edge weights. So we can query any edge in this network, but every query of an edge is expensive. For example, in these transportation network examples. So I'm going to denote a query as a pink dot on one of the edges in this network. Okay, so how can we estimate the shortest path in this graph? So one sort of classic strategy is just to deploy a shortest path finding algorithm, graph traversal algorithm, such as Dijkstra's algorithm in this case. So if we're to run Dijkstra's algorithm on this example, it'll basically access a number of edge weights as it executes, and we can plot the result of running this algorithm. So here, every time you see a black dot, this is one of the edges that's queried within the execution of Dijkstra's algorithm. And the output of Dijkstra's algorithm, the shortest path, is the blue line here, which you can see is exactly the true shortest path between the start and the goal nodes. So this works and it computes the shortest path, but it requires over 430 queries to execute. So intuitively speaking, you might think that maybe we don't need every one of these queries in order to give a pretty good estimate of what is the shortest path in this graph. So instead, we're going to try sort of a different strategy. So suppose here that we take a small set of edge weight queries, for example, 30 uniform at random queries, which I draw again as these black dots. And what we could try to do is infer the shortest path in this network based on this small set of uniform random queries. So in particular, we can do the following. We can use a probabilistic model to infer our black box function f given the set of queries. And then we can run Dijkstra's algorithm on posterior function samples. I'm going to draw the output of Dijkstra's algorithm on each of these posterior samples. So the shortest path that we estimate from one posterior sample as a blue line in this case. So if we do this, we get the following set of blue lines. You can see they're not particularly well aligned with the true shortest path. They're sort of diffuse. But this is the distribution of the output of Dijkstra's algorithm on the set of posterior function samples. So it's not very good, but what happens if we bump up our set of
excuse me, so here the brighter the line is, the more like probable this path is as a shortest path?
Essentially, yes. Yeah. What happened is every posterior sample of the output of the Dijkstra's algorithm, I plotted as the same brightness. But if you have multiple overlapping each other, multiple samples on a given edge, it'll get darker. So that's right.
Yeah. Okay.
Yeah. So this is only 30 uniform random samples. So if we bump it up to 100, we can see if this sort of improves our estimate. And we can see that it does. We start to get more concentrated and brighter lines that are kind of concentrating on the true shortest path, but it's not still not great. And as you can see here, we're taking a lot of sort of uninformative queries that don't give us a lot of information about the output of our algorithm. So namely down here around the edges or up here at the top, at least intuitively speaking, it seems like maybe these don't, aren't very informative, depending on what our probabilistic model is. But in this case, the Gaussian process. So, so what can we do instead? So we want to, choose the best queries to infer the shortest path or to infer the output of Dexter's algorithm. So this is exactly what we care about for running InfoBAX on top of Dijkstra's algorithm as our algorithm A. So if we do this, we get the following animation. So here I'm plotting the sequence of queries that InfoBAX with Dijkstra's algorithm takes, as well as the inferred shortest paths over the sequence of queries. And as you can see, it essentially tries to take a sequence of queries that kind of figure out where the shortest path is and then trace the shortest path as the posterior estimate is converging. So at the end of the day, we get this estimated shortest path after 100 queries of InfoBAX. We can see it's nearly perfect. It's not exactly perfect. It doesn't quite get one corner here, but it's quite a good estimate after 100 queries. And it doesn't spend a lot of samples on parts of the space that are kind of far away from the true shortest path.
Are there actually any samples at all away from this sample path? It looks like it's absolutely certain that this blue line is the path.
Yeah. So I think there are if you take enough posterior samples. For example, I think there might be some that actually do get the true one some of the time, but this was 30 samples, either 15 or 30 samples for this animation, and as you can see, they all pretty much agree, at least for let's say 15 samples, something like that.
So this is not post-processed. It's like you just ran 30 samples, and it's this very bright blue line.
That's right. That's right.
Interesting.
Yeah, and you could say one reason why it might not be perfect here could be because of slight model misspecification, right? So the true underlying function here was not a sample from the Gaussian process prior that I'm actually using here for InfoBAX. It was a sort of a benchmark black box function that people use a lot in Bayesian optimization. So it's not a true draw from that prior. So you could have some slight model misspecification, and your posterior might not exactly be perfect with respect to coverage in terms of the coverage of the true algorithm output. But yeah, the estimate gets pretty good even after 100 queries. So if we want to kind of do a more fair comparison, let's suppose we allowed random search, the original Dijkstra's algorithm versus InfoBAX, to have 100 queries to kind of see their sampling patterns. We can see here the comparison. So in Dijkstra's, the key thing is we basically cut it off after 100 queries, and then we estimated under our Gaussian process the same things we did for InfoBAX and random search. What would be the distribution over shortest paths? So we can see here that it knows the beginning of the shortest path quite well, but it spends a lot of time towards the first part of the shortest path and no queries towards the end. So if we actually kind of try to sample in the most efficient way to estimate the shortest path, we can estimate it much more accurately using far fewer queries. Okay, so the second application I want to talk about is what I call Bayesian local optimization. So the idea here is that Bayesian optimization typically aims to estimate global optima explicitly of a black box function. However, there exists many local optimization algorithms that only aim to find a local optima with respect to some initialization point. For example, gradient descent or evolutionary algorithms or the Nelder-Mead method. And these can be very effective for certain settings, for example, in certain high dimensional settings, or if you have an input search domain that requires a particular type of traversal that your local optimization algorithm gives. But the problem is that you typically need a very large number of queries. Oftentimes these algorithms, for example, make a number of redundant queries. and they're often not very effective if the cost of each query is very expensive. So what we want to do instead is basically use this local optimization algorithms within an Infobacks procedure, which yields some sort of local variants of Bayesian optimization methods, which are parameterized by these local optimization algorithms. So the intuition is kind of you can view optimization as trying to estimate the output of a local optimization algorithm efficiently, given a limited budget of queries, rather than sort of directly trying to estimate a global optima of your space, given a limited budget of queries. So to kind of visualize what's going on here, suppose we have a two-dimensional function with 3 local optima. And if we're to run sort of a simple local optimization algorithm called an evolution strategy here, it initializes at some point towards the top of the screen. It takes a number of random steps till it eventually converges to one of the 3 local minima in this case. And the star is the output of that algorithm. So we can compare this, and this takes about somewhere over 200 queries to converge in this case. And we can compare this to a few different, more efficient sampling strategies that take advantage of a probabilistic model. So first of all, we could sample according to random search, which yields this sampling pattern as black dots, and the pink star is the final estimate of the minima in this case. The second plot in the middle shows max value entropy search, which is a global Bayesian optimization method. So you can see here that the samples start to concentrate around the local optima, but they concentrate around multiple of the local optima, as opposed to Infobacks, which essentially follows a very simpler sampling pattern as the evolution strategy, in that it converges to only one of the 3 local optima. But it just does so using a far fewer set of queries than the original evolution strategy algorithm. So if we run these similar, let me just show this quick animation of the third plot here. This is, again, Infobacks with an evolution strategy. You can see it basically quickly converges to one of the 3 local optima in this case, where I'm showing the estimate of the execution paths in these blue lines as it proceeds. Okay, so if we run this on higher dimensional benchmark black box functions, we can see that Infobacks essentially matches the performance of the original algorithm, which in this case is again an evolution strategy algorithm, but it just does so using far fewer queries. So in this case, we're showing this on a 6-dimensional and a 10-dimensional function, and where we have the iteration on the x-axis and essentially the best achieved value on the y-axis. We can see that our Infobacks method meets the performance of the evolution strategy, which is the orange line here, but using far fewer queries to the black box function. And it also, in these cases, does better than the baselines, which are, one of them is just a sort of a standard max value entropy search global Bayesian optimization method. Okay, final application I just want to describe quite quickly is top K estimation. So suppose we have a large set of items, for example, 500 catalyst materials or bulks in materials discovery. So this is just, imagine we have a set of 500 items here. And suppose that each item has a value under our expensive black box function f. For example, each catalyst might have an activity level, which is quite expensive to measure. We might have to run some sort of expensive computer simulation to measure the activity level of each material bulk. And suppose we want to determine the top K items in this set. For example, the top 10 catalysts that have the highest activity, which we might then pass on to some laboratory scientists who might do further experiments to reduce this set further, for example. So if we want to find these top K items in our set, note that this is distinct from both global optimization, or you can view global optimization as top K estimation where K is equal to 1, but it's also different from level set estimation, which is you could view as finding the subset of the 500 items whose values above or below a threshold. So this is distinct from both of these two examples when K is greater than 1. So visualizing this, suppose here we have a set of 250 items, and suppose that we have a black box function that determines an unknown value for each of these items in our set, and we want to identify the top 10 items here, which I've drawn as gold stars. So these are the top 10 out of the 250 items in our set. And if we want to compute these, we can run a scan and query algorithm where we scan through each of our gray items and we compute its value to find the top K. So again, if we were to do this, each query is denoted as a black dot here, and this will exactly compute the top 10 items in our set. But it, however, uses a number of queries that's equal to the number of items. So in this case, 250 queries. So a new strategy what we can do is make a few queries and then try to infer the black box function and the top 10 items using this set of queries. So for example, suppose we made 10 queries here as black dots, and we tried to do this. I'm drawing the estimated top 10 items as blue squares in this case. So this is a number of samples of the top 10 items. Ideally, we'd want the blue squares to all overlap on top of these 10 gold stars if we had a perfect estimate of the top K. But as you can see, the estimate here is quite bad, using only 10 samples. So suppose we bump this up to 100 uniform random queries of the black box function. If we did this, we can see that the estimate improves. We're starting to get the blue squares to overlap on the gold stars in a few cases, but not in others. And we still estimate that some items over here are part of the set of top 10 items. So this estimate is still not great even after 100 queries. So what can we do instead? We could run Infobacks with our scan and query algorithm. And if we do that, we can see that we get the following sampling pattern as these black dots. And we can see that this gives us a perfect estimate of the top 10 items. And intuitively, what seems to be happening here is Infobacks is exploring sort of the space, at least the whole space at some level of spaced out points, but it's kind of allocating more samples to locations where the function has a higher value or where we have items in order to give a good estimate of these top 10 points. And this can give a good estimate within 100 queries in this case. Okay, so I think we have only 3 minutes left. Actually, can someone tell me will the seminar just go till 3 more minutes or a little bit more?
We can spend, I guess, some extra time if there is something that you need to tell us. But so let's say we have like maybe 10 more minutes, and after which we can stop recording and then maybe discuss something else if some people want to proceed. What do you think about that?
That sounds great. That sounds great. Yeah, I'll just take a couple minutes to describe a slightly related but adjacent topic here. And that relates to the Bayes-opt and Bayesian algorithm execution, but it might be of interest to some people. But I'll go quite quickly through this to spend some time on questions. So the BAX and BO procedures all use predictive uncertainty models, right? A model of the conditional distribution over our output Y given an input X. In particular, we focused on Gaussian process models for BAX, but we may wish to run similar procedures on a number of different types of probabilistic models, and also to know if our models are good. For example, we might wish to run, sort of classic Bayesian models such as Gaussian processes, or various types of linear or nonlinear hierarchical Bayesian models, perhaps different types of neural models such as probabilistic neural networks or Bayesian neural networks, or otherwise, or maybe ensembles or quantile regression or other types of models. And one question is, how do we assess the quality of our predictive uncertainties in these models to sort of use in our Bayesian optimization or Bayesian algorithm execution procedures? So I'm visualizing here basically models that give point predictions versus models that give predictive uncertainties. So on the left here, we have for a test set, I'm plotting predictions versus ground truth values of a given test set of points. We can see when we have a point prediction, we want our predictions to equal our ground truth values, basically points to line up on this 45-degree line here. And if you have a predictive uncertainty model, for every ground truth value, we have both a prediction as well as some notion of the uncertainty of the output. For example, it could be an interval or a parametric distribution or a set of samples as our quantification of uncertainty. If we have some type of predictive uncertainty model like this, how do we assess whether it yields good predictive uncertainty? So there's a few different criteria that we might care about. The first is, for example, accuracy. This is just a quantification for how good the mean or the point prediction is, which is sort of agnostic to this predictive uncertainty, where we want an accurate point prediction. We might care about what's called calibration. So is our predictive uncertainty distribution, is it over or under confident? And this is sort of agnostic to accuracy. You can have something that's well calibrated and low accuracy, or badly calibrated and high accuracy. Finally, another notion that we might care about is sharpness. So on average, how confident are our predictions? Are we, do we have low predictive uncertainty, or do we have in general high predictive uncertainty? And again, you can have different levels of sharpness irrespective of the other two metrics. Okay, so there exists some good metrics for calibration that they're quite useful for different types of sequential decision-making procedures, such as calibration. So suppose, for example, for each test point, we have a predictive uncertainty model that returns an interval, for example, 1 minus alpha interval. We say that something is, that we say that our predictive uncertainty model is well calibrated if this 1 minus alpha interval covers a true value 1 minus alpha proportion of the time for all alpha. For example, suppose our alpha is equal to 0.05, so we have 95% intervals. We'd ideally want our intervals to cover the true value, which is to say the yellow dashed line here, 95% of the time, which we see happens on the left side where we have a well-calibrated predictive uncertainty model. On the right side, we have an uncalibrated model because our this is far overconfident because our 95% intervals do not cover the dashed line 95% of the time. So this is, kind of, you can see how we have a well-calibrated for a particular alpha and an uncalibrated example for a particular alpha. So what you can do is you can scan alpha from 0 to 1. And for each of these values, you can compute the expected fraction of the true values contained in your interval versus the observed fraction of the true values contained in your interval, which gives two curves. And you can compute the area between the two curves. And this is called, for example, the miscalibration area. And so I just want to give a quick plug for the Uncertainty Toolbox, which is something I've been developing with some collaborators to help give a number of tools for predictive uncertainty models. So this is a Python toolbox for predictive uncertainty quantification, calibration, metrics, and visualization, where we aim to provide sort of a glossary of different terms and concepts related to predictive uncertainty, a number of ways of providing metrics and visualizations for different predictive uncertainty models, recalibration procedures, so you can recalibrate a predictive uncertainty model to give better calibration, as well as a number of relevant papers on the area. So another thing that could be useful for people working with predictive uncertainty models for different tasks. Okay, final slide. In this talk, I mainly focused on Bayesian algorithm execution, which you can view as extending Bayesian optimization from targeting global optima to targeting other function properties that are defined by algorithms. I introduced BAX and this information-based procedure InfoBAX. Here's a link to the BAX paper. Please feel free to check it out, as well as to the Uncertainty Toolbox, which we're working on in general to help give tools for predictive uncertainty models. Great, so that is my talk, and thank you very much all for listening.
Thank you, Willie. Now I'm gonna stop recording. Goodbye, everyone.